Okay, so hybridization we know is a mixing of two new orbitals. How do we get to looking at two new orbitals? We need to find its molecular geometry. We need to look at its Lewis structure. Okay, so let's draw the Lewis structure for CH4 and find molecular geometry. All right, so Thomas, what did you have for molecular geometry of CH4?
Tetrahedral.
Yeah, tetrahedral. Raise your hand if you agree. Good. Good. Carbon should be our central atom. Hydrogens can have one bond. Remind me what will get you a frowny face on a Lewis structure.
A double bond with hydrogen, but hydrogen metal bond.
Whoa. I actually understood what you're saying.
Bond with hydrogen.
Uh-huh.
Hydrogen's the center major bond.
Uh-huh. And what else?
And you put lone pairs of hydrogen.
Yeah, putting lone pairs on hydrogen, double bonds with hydrogen, or hydrogen central atom will get you a frowny face. All right. So when we look at CH4 that has a tetrahedral molecular geometry, we have 4 equal orbitals. Okay, but how does that work? Right? If we have an s orbital and 3p orbitals, how do they become equal? Okay, that's what we're going to deal with hybridization. Okay, they're going to make something new. If we look at carbon, which is our central atom, it has 4 valence electrons. Okay, because it's in group 4, we know it has 4 valence electrons. Tell me where carbon's 4 valence electrons are located within those orbitals. Yeah, they're in the outer shell, but what blocks would they be in? What do you think?
There's 2 or in, yeah, one, there's 2 S.
2 in the S block and
2 in P.
2 in the P block. Good. Okay, so carbon has 4 valence electrons. 2 of them are found in the S orbitals, and 2 of them are found in the P orbitals. Okay, this is just a reminder, S orbitals and P orbitals have different shapes. Do you remember the shapes of an S orbital? What's the shape of an S orbital? Sphere. Yeah, it's a spherical. S for spherical. What's a P orbital shape like? Like a dumbbell. Okay, a dumbbell or an hourglass. Okay, that's what a P orbital shape like. So now a hybridization is going to make a new shape of these. Okay, we need to make 4 orbitals to house these 4 domains of our central atom carbon that have equal energies and that have the same shape. Okay, we're going to call this for carbon, or for a tetrahedral geometry, we're going to call it sp3. Okay, because we're using our s orbital and we're using our 3 p orbitals. Okay, so the hybridization for carbon in the CH4 molecule is called sp3. We can predict, or we can find out a hybridization or the electron shape, the electron orbital shape of these new hybrid orbitals is through the number of domains. Okay, it can be non-bonding domains or bonding domains. Okay, we're going to look at the total number of domains. Okay, do you remember what a domain is? Yes, it's anything surrounding the central atom. So it could be an electron or a lone pair, and it could be a bond. Okay, so CH4 has 4 domains. That 4 domain answered leads us to an sp3 hybridization. Okay? We can also predict the hybridization just by memorizing the shape and the hybridization relationship. Okay, so the shape of CH4 we said was what? Tetrahedral. Okay, so any molecule that's tetrahedral will also have an sp3 hybridization. Okay, so there's certain correlations that you can remember, and there's certain patterns that you can follow to go along with the domains. I think that following the domain pattern is a little easier, and I'm going to show you that pretty soon. But you can also just memorize, if it's this shape, it's going to be this hybridization. That's up to you, whichever way you choose. Okay, did everyone get what they need here? Okay. Go ahead and copy this table down in your notes. After you get it copied down, then I'm going to talk about what each of these columns mean, what the patterns look like, and what things you need to kind of recognize when we see this. Okay, the pattern I want to go over with these is that as you look between these 2 columns, this column and the number of domains, you see an increase in the number of hybridization orbitals, the number of hybrid orbitals, right? Do we see an increase? So with a compound that has 3 domains, that means 3 things are bonded or surrounding the central atom. Are we on the same page there? Okay. That means in order to get equal orbitals, okay, equally shaped and equal energy orbitals, we need to use the s orbital and 2 p orbitals. okay, they combine to form 3 equal energy orbitals. So we use an s and 2 p orbitals to get a total of 3, okay, which matches over here. When we need 4 domains, we use an s orbital and we use the 3 p orbitals. To get 5 domains, we use s orbital, 3 p orbitals, and 1 d orbital. Okay? So if you count along with these hybridization numbers, s is 1, we use 3 here, so 1 plus 3 is 4. We use 1 d orbital. That gives us 5 total domains surrounding our central atom, which is what we have. Okay? That's the pattern that I think is a little easier to remember hybridization with. But if you choose to just know that when something's trigonal bipyramidal, it'll be sp3d, then that's fine. Okay? I think the pattern's a little easier to pick up on, though. So if you see an sp3d2 orbital, that means you know that it's going to have 6 domains surrounding it.
So you can just add them all up.
That's the pattern that goes along with it. Because these form 6 equal energy, equally shaped orbitals. Okay, does that make sense? Kind of? All right, let's move on. So an NH3 molecule, take a look at what the Lewis structure looks like. How many domains does it have? 4 total domains. How many are bonding? 3 bonding, and 1 lone pair, which is 1 non-bonding domain. Okay? So 4 domains total will give us what hybridization? sp3. Okay? 4 domains total gives us an sp3. What's the shape of this molecule? Trigonal pyramidal, because it's got 4 total domains. So you look here on the 4, and it's got 1 lone pair, so you move over here and it says trigonal pyramid. Okay? According to our sheet, or according to our table that we just wrote down, if we have trigonal pyramidal molecular geometry, what should our hybridization be? sp3. That means you could go either way and still get the same answer. You can go via shapes, or you could go with number of domains. Okay, both of those will get you to the correct answer if you draw your Lewis structure right and you come to your molecular geometry correctly. Okay? What questions do we have so far? This is what our Lewis structure should look like. Sulfur can have an expanded octet because it has 6 valence electrons to offer, because it's in group 6. Okay, and since it's in row 3, it's got extra orbitals, and this is where we start to look at hybridization. Okay, it's got extra orbitals it can use. So this is how it should look. This is its most stable form. Okay, if we use a single bond on one side and a double bond on the other, it will become what we call a polar molecule, which is what we're going to learn about later in class, and it's a little bit less stable than it is here. Okay, so with this Lewis structure, what would our hybridization be and our molecular geometry? sp2. And what's the geometry? Bent. So if you look at your geometry, is that going to work for sp2 also? sp2 and bent go together? And what about 3 domains and sp2? Do they go together? All right, good. Okay, what about ci4? Jake, what'd you have for hybridization?
sp3.
Good. Okay, Hannah, what'd you have for molecular geometry?
I had tetrahedral.
Yeah, good. On the same page so far? Good. Okay, let's look at our last one. Keaton, what did you have for molecular geometry?
sp2.
For molecular geometry?
Oh, what for
Tell me the shape.
trigonal planar?
Yeah, good. Trigonal planar. And your hybridization was what?
sp2.
Yeah, good. Both right. Trigonal planar, and this was sp2. Okay, a salt molecule and a salt molecule, 2 separate things. Okay, so those are 2 molecules. Intermolecular forces will hold those 2 molecules together somehow. An intramolecular force would be a bond. Okay, that's the attraction that holds atoms together within a molecule. Does that make sense? Okay, I abbreviate intermolecular forces like this, IM. So whenever you see an IM force, that means intermolecular. it's really probably a good idea for you guys to start developing some sort of shorthand as you're taking notes. Okay, little abbreviations like that will help. All right, so intermolecular forces are forces of attraction between molecules, not within molecules. Yes?
What's the shortening thing for molecules?
I want you to think about the process of melting something from a solid to a liquid. What has to happen for something to melt from a solid to a liquid? Yeah, it's got to reach a melting point, but how does it normally do that? Yeah, it's got to heat up. You've got to add energy. Okay, and what happens when energy is added?
More of the things are moving around more.
Okay, they start moving around, right? Things start moving up, they heat up, and when they start moving around, those bonds will break. Those intermolecular forces will break down, okay? So particles, when they're in a solid, they have to be tightly held together by something, right? When they're in that crystal lattice that we talked about, when we're in that solid formation, they have to be held together by something, which are these intermolecular forces, okay? When heat is added, then those intermolecular forces begin to break down, and they don't hold anymore, which means particles can be farther apart, which is what happens in a liquid. So the more energy that it takes to break down these intermolecular forces means that it has a higher boiling point or a higher melting point. Okay, it's going to require more energy to break those intermolecular forces, which would then raise its boiling or melting point. Okay, when we talked about ionic and covalent bonds, which of the following had stronger intermolecular forces? Do you remember, ionic or covalent? Ionic. Okay, because covalents are mostly gases already. So that means that their intermolecular forces have been broken pretty easily. Okay, so ionic bonds have a little bit stronger intermolecular forces. You have some values for melting points and boiling points on page 204 in your textbook. I want you to take a look at those and see relationships on the periodic table, kind of where they respond. Can somebody tell me what a polar covalent bond is?
That's what they share.
They're shared, but they're shared what?
Unequally.
Unequally. Okay, sharing of electrons, but they're shared unequally. Okay, so a bond's considered polar when electrons are shared unevenly between the two atoms. Okay, one is more electronegative than the other, and the electrons shade that way. So that's when a bond is considered polar, okay, is when the electronegativity is between a certain value, okay? What about when a whole molecule is considered polar? Okay, we've talked about polar bonds, but you know within a molecule there can be more than one bond, okay? So when do we consider a molecule to be polar? That's what we're going to look at next. Do you know the names of any polar molecules, or do you know any types of molecules that are polar? Yeah?
H2O.
Yeah. Water is our most polar molecule. Okay? And we're going to look at why. So for a molecule to be considered polar, it's got to have what we call a dipole moment. Okay, it sounds really dramatic, right? A moment. I don't know why it's called that. But it's called this dipole moment. So it means equal but opposite charges are separated by a short distance. When one element wants an electron so bad, it becomes kind of a partial positive charge or a partial negative charge to draw those electrons in. Okay? A molecule is also considered polar when it's asymmetrical. Okay? When it doesn't have complete symmetry, it's polar. So that's a really good clue indicator for us. You might want to underline that in your notes or something. Anytime a molecule is asymmetrical, it's not 100% symmetrical, then it's polar. Okay. So if we look at water, we might kind of think that it's symmetrical, right? Because we can draw a line of symmetry right down the middle and it looks symmetrical, right? But what if I draw a line of symmetry right here? No. What if I draw a line of symmetry right here? No. Okay? So it's got to be 100% symmetrical from every angle. Water doesn't work like that because it's polar. It is asymmetrical, so it's polar. Okay? Let's look at the Lewis structure for HCl. I want to talk about a dipole moment here. Let's look at the Lewis structure for HCl. Okay? It looks like this. Group 7s like to have 1 bond and 3 lone pairs. Okay, total we should have 8 valence electrons, and I see 2, 4, 6, and 8. So this is our Lewis structure for hydrochloric acid. Okay, here's where the polarity part of it comes in. Which of these two molecules, or which of these two atoms is more electronegative? Yeah, chlorine. It's closer to fluorine, so that means it's more electronegative. So what we do when we're trying to determine polarity is we're going to take and draw an arrow in the direction of the most electronegative atom. Okay, so we're going to draw an arrow toward the most electronegative. So chlorine is the most electronegative atom, so we're going to draw an arrow towards chlorine, and we're going to put a little positive end on the least electronegative atom of those bonds. Okay, so here we only have 1 bond that we're looking at. The most electronegative is hydrogen, so we put the little plus tail of the arrow, and then we're going to put the head of the arrow, or the tip, at the most electronegative, okay? The one that wants the electrons more. Okay? Since chlorine is so electronegative, it draws those electrons in the bond towards chlorine enough that it becomes what we call a partial negative. And hydrogen becomes a partial positive. Okay, so that's kind of a delta. It's a Greek letter. It looks like this. It's like an S with a little tail on it. Kind of looks like a Hershey's Kiss if you look at it the right way. That's a delta. Okay, and it means partial in this situation. So this chlorine wants electrons so badly in this bond that it's hogging them towards this side. That extra electron from the bond on chlorine's side makes it kind of have a partial negative charge. Hydrogen becomes a partial positive charge because it's lacking that electron. So in this molecule, since there's only 1 bond, this also becomes our overall polarity arrow, which is called a dipole moment. Okay, so this is our overall dipole moment right here. We're going to look at molecules that have more than 1 bond, which may have more than 1 polarity arrow like this, and we'll see how to determine the dipole moment for those molecules. But for right now, since we only have 1 bond, this is our dipole moment, which means this molecule is polar. Okay? And it's asymmetrical. So you also know it's polar from that way. Okay? Yes? No? All right, we're going to watch, we already talked about this. Okay, let's try a couple more. We talked about water already. We don't need to go through all this because we already did it. Okay, we're going to look at the dipole moment for water. We determined that it was polar just based on the fact that it's asymmetrical, but we're going to determine its polarity and its dipole moment. So for our H2O molecule, oxygen here, okay, so now let's look at our individual polarity arrows. Okay, we have a polarity arrow for every single bond. For every bond, okay? So where should our arrow start in this bond? And where should it go to? It should go from hydrogen to oxygen because oxygen is more electronegative. So it would look like this. And we put our little plus sign at our least electronegative. What about this bond over here? Yeah, it should look the same. So we'll draw it towards oxygen, and we'll put our little plus sign on hydrogen. So now we have 2 polarity arrows in our molecule, but we don't have an overall yet. How can we combine these arrows to make one overall dipole moment?
Can we get H2? No, it already is H2. Dang it, never mind.
These are both going to the middle and up, right? So our overall dipole moment will look like this. Straight up through the middle. Okay? That's what our overall dipole moment would look like. Okay? And if we want to put our partials on our hydrogens, would hydrogen be a partial positive or a partial negative? Yeah, partial positive because it's kind of losing that electron toward oxygen. And what about oxygen? Would it be a partial positive or partial negative? A partial negative 2. Because it's getting an electron from each of those. So let's go ahead and try these couple. Figure out if they're polar or nonpolar. Okay, this first one is CCl4. Okay, so carbon tetrachloride. And the second one's NaCl, or sodium chloride. Yeah, nonpolar. It's nonpolar. Why do we think it's nonpolar?
Because it's symmetrical.
Yeah, it's symmetrical. Okay, and if I'm going to draw my polarity arrows, they're all going to go toward chlorine. And that means our top ones will cancel out and our side ones will cancel out because they're pulling with equal magnitude or with equal strength in opposite directions. Okay, so it's kind of like a tug of war. If they equal out on both sides, then nothing's going to happen. Okay, this is a non-polar molecule. Okay, and it's totally symmetrical.
So you have to put the little arrow things even though it's not polar?
Yeah, you don't have to. If we would rewrite it, it doesn't have a dipole moment, so no, you don't need them. Yeah. Okay, and what about NaCl? What do you think?
I think it's not polar.
Yeah, Keaton, what do you say it louder? It's ionic. It's not polar or nonpolar because it can't be. It's not a covalent bond. Okay, sodium and chloride. Sodium's a metal. Chlorine's a non-metal.
Be a polar or something.
Metal and a non-metal is an ionic. Yep. It can only be a polar. It can only be a polar bond if it's a covalent bond. There's no sharing of electrons here. So listen, what happens here is NaCl. Okay, sodium completely transfers that electron to chlorine. So chlorine has a -1 charge, sodium has a +1. Okay, that's an ionic bond. Okay, we transfer that electron, so that's what our Lewis structure would look like there. It just looks like this. Basically, sodium has no electrons because it gave its 1 to chlorine. Okay? All right. Let's look at some different types of intermolecular forces, okay, like hydrogen bonding he talked about. This is the book definition of a hydrogen bond, okay. What it says is that it's an intermolecular force in which a hydrogen atom that's bonded to a highly electronegative atom, such as oxygen, fluorine, nitrogen, chlorine, okay, things like that, those are highly electronegative. That hydrogen molecule will become attracted to a lone pair of electrons of an electronegative atom in a nearby molecule, okay? And that's a lot of words for a pretty easy definition, okay? What it's saying is that hydrogens in polar molecules are attracted to the partial negatives of another polar molecule, okay? Hydrogen bonding is not a real bond, it's a strong attraction. That's what's meant by this dotted line down here. Okay, here's a covalent bond between oxygen and hydrogen in a water molecule. Okay, we looked at our water molecule earlier. Our hydrogen would have kind of a partial positive here. So that would be a little partial positive. Our oxygen would have our partial negative. And this oxygen has a partial negative. Okay, so this partial positive and partial negative here are attracting each other via that hydrogen bond. Okay, and hydrogen bonds are strong, but they're not truly a bond. Okay, there's no sharing of electrons, there's no transferring. It's just a positive charge and a negative charge attracting each other. Okay, they're usually represented by dotted lines like shown in this picture, and it causes hydrogen-containing molecules to have high boiling points because hydrogen bonds are difficult to break. Okay, this attraction between a partial positive and a partial negative are difficult to break. Okay, so it causes things to have high boiling points and high melting points. Any questions on hydrogen bonding? We're going to talk about our last type, and then that's it for notes for today. Yeah, Hannah?
What was your short?
Okay, so a London dispersion force is an intermolecular attraction that results from constant motion of electrons and the creation of instantaneous dipoles. Okay, these are very, very weak attractions, but they occur everywhere, all the time. Okay, these are the only forces that occur in every type of molecule, every type of bond. These occur all the time, everywhere. Okay, and the way these work is that electrons are in constant motion. Okay, when we draw our Lewis structures, we draw them in a set place, but in real life, they're in constant motion. Okay, so as electrons are moving about, they may be sliding towards one atom and then another, and then one atom and then another. So it's going to create these little instantaneous dipoles, right? A partial positive and a partial negative. Those instantaneous dipoles will attract one another for just an instant, and then they'll switch to something else. Okay, so that's what these London forces are. They're very weak, and they're very short-lived. Okay, but they happen all the time. Okay, so London dispersion forces are the weakest intermolecular forces of all. Okay. They act between all atoms and molecules, but they are the only forces that act between nonpolar molecules and noble gases. Okay. That's why nonpolar molecules are pretty easy to break up, and gases are obviously already gas, so it doesn't take a whole lot of energy to make those into the gas phase. All right, and this last bullet says London forces increase with an increasing number of electrons, which means they would increase with molar mass. Okay, so the strength of London forces increase with molar mass. Okay, because as molar mass increases, that means the number of protons increases, which means the number of electrons increase. Okay, when the number of electrons increase, that means there's more movement between them, more instantaneous dipoles which become created, which means more London forces. Okay, so as you go down the periodic table, radon has a greater boiling point than helium. Okay, because there's more protons, more electrons, and they would have greater forces, greater intermolecular forces to try and break apart. Okay?